Good evening, folks, and welcome to the stream. We are just about 5 minutes out from the release of the puzzles for day 22 of Advent of Code. Looking forward to solving those along with you this evening. As always, I'm going to be working through solutions in C++. You can always find the code that we write in these streams up in my GitHub repository at github.com/Craig-Chasseur/AOC2020. I've put the repo up on the screen there. You can also always find stream replays up on my YouTube channel at youtube.com/spoonboy42. As always, if you have any questions, feel free to drop those in chat. I'll do my best to answer them. Or if you're watching the replay later on YouTube, feel free to leave a comment, and I'll do my best to answer you there. So, we have just under 4 minutes now until tonight's puzzles unlock. So, we might as well do just the little preliminary part of setting up the basics for a puzzle solution here. So I'm going to make a new directory for day 22. And inside that, we'll make just a bare bones C++ program. Oh, I did not mean to make that a directory. Let me delete that. Meant to make that just a file. Part1.cc. There we go. So we'll make just a minimal C++ program here. And eventually we'll code up our solution in here. And then we will make a build file so that the Bazel build system that we're using knows how to build this. Okay, and let's go ahead and build and run that and make sure that everything's working okay. Okay, there we go. Returns nothing, as we expect. So almost every day we wind up using a couple of the utility libraries that I wrote that I have in my repository here just to do file I/O to, read in some input files, and this check routine, which we use to do assertions that are always present no matter the build configuration. So let's go ahead and include those. And we will go ahead and put those dependencies in the build file. And again, build and run. And everything looks like it's good to go. So we have about a minute and a half until tonight's puzzles unlock. We've been revealing more and more of the image of our circuitous route to try and get to our island vacation. So last night, remember the puzzle was about stocking up the handmade raft that we're going to try and sail the remaining portion of our trip to our destination on by figuring out all the ingredients in food that correspond to different allergens. So I'm interested to see what we do tonight. I think the puzzles have definitely been getting a little trickier, a little more difficult. For sure, day 20, the puzzle arrangement, the actual literal jigsaw puzzle that you had to have the program solved was definitely a tricky one, which I think it was for a lot of people. Day 19, I think a lot of people found that kind of difficult, where you could have that recursive grammar of strings, but the way that we happened to write it actually made it relatively easy to solve the second part of that. And then last night's allergen one was, there were some tricks to it, but I don't think it was nearly as difficult as day 20. But we shall see how day 22 goes for us right now. Crab combat. Okay, we brought a deck of space cards. Oh my gosh, we had these from last year. Combat. We're going to play a game with the crab. Split the cards so each player has their own deck. Okay. Both players draw their top card, and the player with the higher value card wins the round. Winner keeps both cards, placing down the bottom of their own deck so that the winner's card is above the other card. It causes the player to have all the cards they win, and the game ends. Okay. Okay. So this is also, you may also recognize this as the card game War, depending on where you grew up. Once the game ends, you calculate the winning player's score. The bottom card in their deck is worth the value of the card multiplied by 1, second from bottom by 2, and so on. Okay. All right. So part 1, at least, I think is going to be relatively easy to figure out. We just simulate the entire game until it finishes. Yeah. So we'll save our day 22 input there. Let's see what it looks like. Okay. All right. Let's first write some I/O to actually read those cards in. So we'll go ahead and check that our program gets exactly 2 arguments, one for the program name itself and one for the input file name. We'll read in the lines using this read lines from file function that I wrote earlier. We will split these up by the empty line so that we get the player 1 and player 2 decks. So there should be just 2 of those. And then now we could represent the decks as literal decks. I think, or maybe we'll use the Q wrapper class. Let's see here. Is Q going to give us everything that we want, or do we want to actually use a deck? Yeah, let's go ahead and use a deck. So we'll use a deck to represent a deck. So deck in this case is the C++ standard library's double-ended queue class. And because we want to be able to look at things on the top, put them back on the bottom, we could do that with just a regular queue, but when the game ends, to score it, we're going to want to actually iterate through all of the items without necessarily popping them. So let's so we'll do it this way. So, to actually run the game, we'll say, while neither deck is empty, We look at the top card of each. Does it have a procedure for breaking ties, I wonder? Let's see. Or are the numbers arranged so that there are no ties? I actually think that that might be the case. That the numbers are arranged so that there are no ties. Okay, so we'll just say if so if player 1, if the front card on player 1's deck is less than the front card on player 2's deck, player 2 wins this round. And so we will rotate the stuff around to the back of player 2's deck. So we'll say push back, and the winning card goes above the losing card. So we'll push back the front card from player 2's deck. We'll push back the and then the front card from player 1's deck. And then we should remove those two front cards to reflect that we put them around on the back of player 2's deck, but we're actually going to do that outside of this if statement, because no matter who wins, we are going to do same thing. So if player 1 wins, we just reverse the order. So player 1's card goes front, and then no matter who wins, we remove the front card from each deck. Okay. So now let's get back to finishing up processing our I/O. So we can say we've got player 1's deck here. And the first line for each of these, well, we can actually check. Just say that check decks dot front. The first line of that should just say player 1, so that we see that their whole deck. So we just iterate through all of those lines, which are just numbers represented as strings, and we will parse those into numbers. Although, yeah, we want to start one past the beginning, because that beginning will be that player 1 string. Okay. Actually, let's maybe, since we need to do this twice, we'll just make a parse deck routine. Okay. And then we do just the same thing to parse with the other group of strings to parse player 2's deck. Then we run the game. With both players' decks. And then we have to just calculate the winning player's score. So let's just see here. Yes. All right. So we'll write another routine to score a deck. And so we have 1 times the back card in the deck, 2 times the next to back, and so on. The multiplier goes up each time. So we'll just sum things up that way, and we'll go through the back. And because we're starting the multiplier at 1 for the back of the deck and counting it up through each time, we'll just go through the deck backwards. So we can use that with R begin and R end instead of begin and end. That gives us reverse iterators that just go through the deck in backwards order. So for each of these, we multiply sum by value of that iterator times the value of the multiplier, and actually we can do mul plus plus because we want to increment it after each time. And then we return that sum, and that gives us our score. So we say, so now we can say if we can say if player 1's deck is empty, then player 1 lost. So we want to score player 2's deck. Otherwise, player 1 won, and we score player 1's deck. And then we just print out the score for the winner. Okay, I think that's all we need for part 1. String should be in here too, shouldn't it? We use the strings library from Abseil, but nothing else. So we'll make sure we have that dependency in our build file. And let's go ahead and give this program a little check using the sample input on the website and see if it gives us the same answer before we try it with our actual puzzle input. Okay, that gives us 306, which is correct. So let's try it with our actual puzzle input. 30,138. A very good score for whoever won, which I neglected to print out. But we don't actually need that to get the answer to the puzzle. Let's see if we got it right. We did! All right, on to part 2. Okay, we lost to the crab. Crabs aren't very good at recursion. To defend your honor, you challenge the small crab to a game of recursive combat. Aha. Still starts by swing cards in 2 decks, playing the same starting decks as before. Game then consists of a series of rounds with a few changes. Before either player deals a card, if there's a previous round in this game that had exactly the same cards in the same order in the same player's decks, the game instantly ends in a win for player 1. Previous rounds from other games are not considered. This prevents infinite games of recursive combat, which everyone agrees is a bad idea. Okay. Otherwise, this round's cards must be in a new configuration. The players begin the round by drawing the top card of their deck as normal. Both players have at least as many cards remaining in their deck as the value they just drew. The winner is determined by playing a new game of recursive combat. Otherwise, at least one player must not have enough cards left in their deck to recurse. The winner of the round is the player with the higher value card. Whew, boy. As in regular combat, the winner of the round, even if they won the round by winning a subgame, takes the 2 cards. During a round of recursive combat, if both players have at least as many cards in their own decks as the number of the card they just... Wow, these rules are complicated. I'm going to have to read these a couple of times. If both players have at least as many cards in their own decks as the number of the card they just dealt, the winner of the round is determined by recursing into a subgame of recursive combat. Yeah. Player creates a new deck by making a copy. Okay, so we're not necessarily dealing with the same deck. We're copying them. The next card's in their deck. Game that triggered it is on hold and completely unaffected. Okay. Ooh, boy, okay, this is a tricky one, but I think we, depends on how deeply we recurse, but I think that this, I mean, let's just try and implement these rules. So first thing I'm going to do is copy the solution that we have for part 1 over to start our solution for part 2. And we'll make a new build target for that in our build file. So, looking at the rules of recursive combat, I'll just refresh this here. So we've got run game here. And this says, before either player deals a card, if there was a previous round in this game that had exactly the same cards in the same order, in the same player's decks, the game instantly ends in a win for player 1. So the way that we can keep track of that is we will use a flat hash set here, where the keys are pairs of the decks. And fortunately, the Abseil hashing framework is compatible with all these standard library container types like pairs and decks. So these are all just automatically hashable and would have the behavior that you would expect. Huzzah. So we say scene configurations. And each time we go through an iteration of this game loop, we're going to try to insert it into the set of scene configurations. And if we find that there is a duplicate configuration, then we're going to stop the game right there and instantly player 1 will win that game. So going to try to emplace that pair of the two players' decks. If we fail to do that, player 1 wins immediately. And I'm going to change this run game method. Yeah, I'm going to change this so that we pass in the decks by value, and it returns the winner's deck. Because we're going to be making copies and everything, it no longer makes sense to just try and modify all of this in place. And we can also wind up in a win situation where neither player's deck is empty yet, but we still need to know who won. So we'll pass back the winner's deck. So player 1 automatically wins if we repeat a configuration of this game like this. Otherwise, yeah, we're in a new configuration. So I'm going to go ahead and take the cards off the deck right away in this case. Okay. So if both players have at least as many cards remaining in their deck as the value of the card they just drew, we have to play Recursive Combat. So if the value of player 1's cards is greater than or equal to the remaining size of their deck, and the same thing is true for player 2, then we play Recursive Combat. Put that in for player 2. Now, I'm going to punt on that right now and come back and write that. But then we'll go ahead and continue, because we would go into the next, because after we play Recursive Combat, we're going to go around to the next iteration of this level of combat. Otherwise, the winner of the round is the player with the higher value card. So we implement the basically the same logic as we did before, except that, now we've already popped the cards off. So if player 1 card greater than player 2 card, well, I guess I'll do less then. We could just do it exactly the same pattern as we did before. In this case, player 2 wins. And we put their cards on the back there. Oh, well, we have to do that in 2 separate statements. Otherwise, do basically the same thing, except we award these to player 1. Can probably make these consts, too, I realize now. Okay. So, and then ultimately when we get out of the loop, we will return... So if we terminate this loop due to one of the player's decks becoming empty, we will go ahead and return the non-empty deck. So Now for the potentially kind of tricky part where we have to actually play recursive combat. Each player creates a new deck by making a copy of the next cards in their deck. So the winner of the round is determined by the winner of recursive combat. But we need to make run game work recursively. It's not going to. We need it to not just return the winning deck. We also need it to return who won. So just make an enum to represent that. And we will have a struct to represent the winner that consists of player and their deck. So at this point, we then change it to return turn the winner that way. And down here, we similarly will return the structs to indicate winners of recursive combat. Neaten that up. Okay. So for recursive combat, all that we need to do is make these subdecks. So we can just make the subrange from iterators here. And we, again, use the value of player 1's card to tell us how many cards to put in that subdeck, which is a copy. Doesn't affect the outermost game here. Do the same thing for player 2. Now, we find the recursive winner here by calling run game again with these two subdecks. And so say if the winner of that subgame actually, since the logic for rotating the cards around is the same, what I'm going to do here is say just player round winner initially. Then we can just say winner equals the winner of the subgame. Oh, should be player as that field. So we found all the ways that a winner of this round can be determined, and then we just go ahead and rotate. So in this case, it should be if we rotate them around to player 1, and as I recall, the winning card should go above, so that should be pushed first. Otherwise, player 2 takes the cards. And player 2's card goes on top. Okay. I think we have our recursive implementation of the game. So now we just need to run the game here with the new version of run game that supports recursion. Move the decks to avoid a copy here. And for the score, we'll just use that winner's deck. So I think that this may actually be our part 2 solution now. Let's try it. On that initial test input. We need to have a dependency for flat hash set, since we use that now to keep track of game states. Segfault does not look good. Just gonna look at the rules here real quick. Make sure. Yep, okay. Let's go ahead and build that with debugging symbols. And run it under the debugger and see what happens. Okay. Look at our backtrace here. Somewhere where we're putting... Okay. Line 37 here. Where we are making these subdecks. So we should only be in here if player one's card is greater than or equal to their deck size. Oh, player, that can't be the right card. Cards can't be huge like that. So that kind of indicates to me that there's some kind of corruption elsewhere where we're not setting or not or something is wrong here, because that value can't possibly be right for one of the cards because they only go up to 10. Player 2's card looks sensible, at least. So maybe we want to add a little more logging. Going to add just some logging so that each iteration of this we'll see what the actual decks look like and maybe see where we go wrong. Of course, we should do that for player 2's deck as well. Yeah. Okay. So kind of right away we get into this problem of right after the first round we get this big number, which doesn't make any sense, and then we start rolling zeros in here. These are backwards. The really simple thing, but the number of cards... Yeah, these are backwards. The size of the deck has to be greater than the cards, not the other way around. That was the whole thing. Simple little thing, but with possibly big consequences. So we could get 291 for the result on that, which is correct for that test input. Let's see what it does for our actual test input. Okay. It is taking more time now. And I wonder if we have to do... Oh, okay, we got to an answer there. 31,587. Should I be suspicious of... Is that... That sounds familiar. Okay, it's not the same as first. Let's go ahead and take that result and see if we are correct. All right! And we made the top 1,000. Just barely, but we made it. Because we, struggled with that, low problem there. So, again, you got to see me use the debugger a little bit more today to try and figure out an error. That segmentation fault was happening because we were trying to go far beyond the actual memory of the deck. Because we had, we had read some corrupted memory. We had really read beyond, we'd read beyond the end of the decks a couple of times. And, yeah, so the really key thing I would say is that, we just missed the direction of the comparison one way or the other. But, with a little bit of debugging, we figured out what was going on and got to our answer. So this was another pretty fun puzzle. I think I thought it was relatively easy, to just implement this recursive version of the game. I think that maybe potentially the hard thing that people might have gotten stuck on was making sure that you never see the same configuration twice. But because we're using these abseil hash-based containers in the abseil hashing framework, flat hash set using abseil hash already knows how to hash pairs of things, already knows how to hash decks of things. So just recording all the configurations of the game that we've already seen for this part is super, super easy. So, being able to hash composite types like that makes a big difference. So that'll be about it for tonight. Thank you again, everyone, for watching the stream. You can, once again, always find the code that we write in these sessions up on my GitHub repository. That's github.com/Craig-Chasseur/AOC2020. Stream replays are always up on my YouTube channel at youtube.com/spoonboy42. These live streams we do every night at about 9 p.m. Pacific time are on my Twitch channel. You can find all the links to all that stuff down in the description. So once again, thank you very much for watching and joining me as we work through these puzzles. And I will see you again tomorrow night as we roll through the last few days of Advent of Code. Good night, everyone.